Good morning to all of you. In this lecture, we will discuss about the basics of electric field. What is electric field? What is its unit, dimension, and what is electric field lines, or what is the property of electric field lines? And I will also discuss the expression of electric field for a discrete charge system and continuous charge system. So in electrostat, we have two different kinds of charge: source charge and test charge. So what is electric field? The first question is, what is electric field? It is represented, this is a vector quantity, it is represented by letter E vector. So electric field is a region of space or region of charge space in which if you will bring another charge, it will experience a force. So this is one definition. Another mathematical definition of electric field is electric field is force per unit test charge. Force per unit test charge. It is a vector quantity. Its unit is Newton per coulomb. And next is electric field lines. So what is field lines? So electric field line is one of the way to visualize the electric field. It has some property. The first property is it originates from the positive charge and terminates at negative charge. Second, originating from positive charge and terminate at negative charge. Second property, electric field line never intersect. So E lines, electric field lines never intersects. We have third, the electric field lines never intersects. So how to draw the electric field lines for a single point charge, or a two equal and opposite charge, or two equal charge situations? So let us draw the field lines. So draw the electric field lines for case 1, single point charge. Single point charge. If we have a plus Q charge, this is plus Q charge. So what is the nature of electric fields? So electric field is away from this charge. Electric field lines away from this positive charge. If it is negative, then electric field lines coming towards the charge. So we have two different situations. One is due to positive charge and another is due to negative charge. So we can draw field lines due to a single point charge. Now what happens if we have two charges of opposite, two equal and opposite charges? Two equal and case B. Let me write here. Case B. Two equal and opposite charges. Let's say we have a plus minus Q charge. This is plus Q and this is minus Q. So how to draw the field lines corresponding to, for a single point charge, it's okay. We have for positive charge field lines away from the charge, and for negative single point charge field lines towards the charge. Now what happens in this case? So we know the property of electric field line that it originates from the positive charge and terminates at negative charge. So with this analogy we can, so electric field lines originate from the positive charge and terminates at negative charge. So this is the way to draw the field lines. To draw the field lines. So this is the schematics of electric field lines due to two equal and opposite charges. Now what happens if we have another case? How to draw two equal positive charge? So how to draw the field lines or field patterns in this case? That if we have two equal and positive charge, then how to draw the field lines in both the cases? So electric field lines, electric field vectors away from the charges. And they will never intersect each other. We know another property of electric field lines. So this is another way to represent the. So we have three different situations in which we have discussed how to draw the electric field lines. If we have a single point charge, then the electric field lines is following this profile, means it is coming out of this charge, and if you have negative single point charge, then electric field line coming towards the charge. If we have two equal and opposite charges, in this case we have this profile that electric field lines originate at positive charge and terminate at negative charge. But if we have a two equal and equal positive charge, or converse is also possible if we have a two equal negative charge. So if we have a two equal positive charge, the pattern of electric field lines are this way. We can. So by symmetry we can draw. So these are the schematics and these are the property. So we have few more properties that electric field line originate at positive charge, terminate at negative charge. Next, it never intersects to each other. Higher the density of field lines, and the property higher the density of field lines, stronger the field. Stronger the field strength. So it's all about the proper what is electric field and what is the electric field lines. Next we will discuss about the expression of electric field for a discrete charge system. So electric field expression for a discrete charge system. So let me write point 1 for discrete charge or discrete charge. So consider if we have several point charges. So consider if we have several point charges Q1, Q2, Q3 dot 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 Q1, which are separated by a distance, R1, R2, R3 dot 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 Rn. Then total force on the test charge capital Q due to these source charges are F1, F2 dot 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 Fn. So total force is F is F1 plus F2 plus dot dot dot. We know the force profile is F equal to Q upon 4 pi epsilon 0 Q1 by R1 square R1 cap, Q2 by R2 square R2 cap plus dot dot dot. If you have n number of charges, then this becomes Q1 by Rn square Rn cap. So F equal to, we know the, so what is electric field? So electric field is E equal to F by Q, which is 1 upon 4 pi epsilon 0 summation I equal to 1 to n Qi by Rn square Rn square. So this is the profile of electric field for a discrete charge system. And this E is called electric field of source charge. Electric field, this is vector quantity. So electric field of source charge. So what happens if in this case we have a discrete charge system? For example, we have a Q1, Q2, Q3 charges which are separated by a distance R1, R2, R3, R dot 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 Rn. Then force experienced by these charges are F1 corresponding to Q1, F2 corresponding to Q2, F3 corresponding to Q3 dot dot Fn corresponding to Qn charge system. Means how much force exerted by these source charges on test charge capital Q. But what happens if the charge is not discrete? If the charge is along the distributed, if the distribution of charge is continuous, if we have a continuous charge distribution, so if the charge is distributed continuously, if the charge is, for example, if the charge is distributed along the wire, along the surface, along the volume, then we have a different profile of electric field. So let us discuss what is the expression of electric field for a continuous charge system. So E expression of electric field for continuous charge system. So there is relation between discrete and continuous system. So the electric field profile for a continuous system. So summation changes into integration. This is summation and this is integration. So for a continuous system, summation changes into integration. So electric field profile is 1 upon 4 pi epsilon 0 dq by r square r. This q is replaced by this expression. So this is the profile of electric field for a continuous charge system. Now we have three different situations. If the charge is distributed along the line, again case A, if charge is distributed along line, which is one dimensional situation, So what is the profile of dq? See, we have a different profile of dq. If the charge is distributed along the line, we have different expression of dq. If the charge is distributed along the surface, we have different profile of dq. If the charge is distributed along the volume, we have again different profile. So depending upon the different profile of dq, we have three different profile of electric field, which means we have an entirely different expression of electric field corresponding to line charge, corresponding to surface charge, corresponding to volume charge. So let us see it one by one. So if the charge q is distributed along the line having line charge density lambda, so the wire head, if the charge, and we want to find out the field at any point P whose length is, so consider a length element dl along this wire, and we want to find out the electric field at any point P which is at a distance r in terms of lambda. The line charge density of this wire, the line charge density is lambda, and lambda is charge per unit length. Lambda is charge per unit length, which is dl. So dq is lambda dl. So this dq is lambda dl. This dq is lambda dl. Now, so we have electric field profile corresponding to line charge density is 1 upon 4 pi epsilon 0 lambda dl by r square r. Now case B, if charge is distributed along the surface, it means charge distribution is 2D, and we have a concept of surface charge density. Surface charge density, in this case we have a concept of surface charge density, which is sigma, charge per unit area. So we have a surface charge, consider a small elemental area dA, and we want to find out the field at this point, and this surface having surface charge density sigma. Sigma, which is dq by charge per unit area, dq by dA, which implies that dq is sigma dA. So dq is sigma dA. So what is the electric field profile corresponding to surface charge? So E surface is 1 upon 4 pi epsilon 0 dq is sigma dA by r square r. Now we have third case. The third case is if the charge is distributed along the volume. So in this case we have a concept of volume charge density. We have a concept of volume charge density. So consider a small elemental volume and we want to find out the field at any point P due to this volume element dV. So we in this, if the charge is, this is volume for along volume or throughout the volume. Throughout the volume. If the charge is distributed throughout the volume, so in this case we have a concept of volume charge density. Volume charge density, which is rho. So rho is dq by dv, which implies that dq is rho dv. So electric field profile for a volume charge density, or in another way we can say that the expression of electric field for the case of volume charge, if the charge or if the charge is distributed throughout the volume, in that case our electric field profile is 1 upon 4 pi epsilon 0. This is dq and dq is rho dv. This is volume integral by r square r. So depending upon the nature of distribution of charge, we have three different but profile of electric field, but in discrete system we have one profile which is E equal to 1 by 4 pi epsilon 0 summation I equal to 1 to n qi upon ri square r cap. But in this case we have three different profile: E volume, E surface 1 upon 4 pi epsilon 0 sigma dA by r square r cap, E line rho lambda dl. This lambda is dl by r square r. So we have three different profile of electric field, and we can correlate our dq is, this dq is lambda dl, this dq is sigma dA, this dq is rho dv. This is very important parameter, and this will tell us the actual distribution of charge. If the charge is distributed along the line, then dq is lambda. This is lambda dl. dl is the length element. If the charge is distributed throughout the surface, in that case our dq is sigma dA, where sigma is a surface charge density, which is charge per unit area. If the charge is distributed along the volume, so dq is rho dv, where rho is the volume charge density, and which is dq by dv, charge per unit volume. Next we will discuss the few examples which is based on this concept. So calculation of electric field in different situations.